So when you hear the word mathematics, what's the first thing that pops into your head? Is it multiplying huge numbers, or maybe just a fuzzy memory of formulas from school? Well, today, we're going to pull back that curtain and show you what math really is. And trust me, it's way more creative and powerful than you probably imagine. You know, most of us have this idea that mathematicians are just human calculators, doing super complicated arithmetic all day. But honestly, that's a total myth. The real heart of mathematics isn't about calculation at all. It's about certainty. It's about being able to prove that something is absolutely 100% undeniably true. Okay, think back to school. We all learned about right-angled triangles, right? And I'm sure you remember the Pythagorean Theorem. It's probably one of the most famous facts in all of math, connecting the lengths of those three sides, A, B, and C. Your teacher told you a squared plus b squared equals c squared. And you used it, you memorized it, you passed the test. But have you ever stopped to think, how do we know that's true? Not just for the triangles in the textbook, but for every single right-angled triangle that could possibly exist anywhere in the universe. See, for a mathematician, just testing a few examples is nowhere near good enough. And that right there, answering that question, is what math is really all about. It gives us a toolkit for establishing absolute, unshakable truth. And the number one tool in that kit, it's called a proof. It's a rock-solid argument that leaves absolutely no room for doubt. So let's actually see one in action. We are going to prove the Pythagorean theorem right here, right now. But not with a bunch of boring algebra. We're going to do it with a simple, visual argument. It's a fantastic example of how beautiful and, dare I say, elegant a proof can be. All right, take a look at this picture. Seems simple, right? It's just a big square with a smaller, tilted square nestled inside. But believe it or not, this one single image holds the entire key to proving that theorem once and for all. Let me walk you through it. Okay, so the whole trick here is that we're going to calculate the area of that big square in two different ways. First, the easy way. The length of a side is just a plus b, right? So the area is a plus b squared. Simple. Now for the second way, let's just add up the pieces inside. We've got the four triangles and that tilted square in the middle, which has an area of c squared. Now, since both methods have to give us the same total area, we can set them equal to each other. A little bit of algebra later, and voila, you get the undeniable result. A squared plus b squared equals c squared. And that is a proof. It's a perfect chain of logical steps, starting from things we already know, that leads us to a conclusion that nobody can argue with. It's a feeling of pure certainty. Pretty satisfying, isn't it? But, and this is a big but, here's where things get a little tricky. Just because an argument uses a bunch of math symbols and looks like a proof, that doesn't automatically make it correct. One tiny hidden flaw can make the entire argument come crashing down. So, for this next part, I need you to put on your detective hat. I'm about to show you a proof, and your mission, should you choose to accept it, is to find the crime, that one single fatal error hiding in the logic. Okay, you ready? Here's the claim. Using math, I can prove that 1 equals 2. Now that should immediately set off all kinds of alarm bells in your head. We all know that's false, which means there has to be a mistake in the argument somewhere. The only question is, where is it? Okay, let's follow the steps together. We start by saying, let x equal y. Fine. Then we do some pretty standard algebra. We multiply by x, we subtract y squared from both sides, we factor both sides. I mean, all of this looks perfectly fine, right? Then we cancel out that x minus y term on both sides, substitute x back in, and we get 2 equals 1. Every single step looks valid. So what on earth went wrong? I'll give you a second here. Take a really close look at step 5. What are we really doing when we cancel that term from both sides of the equation? And there it is, the smoking gun. Remember way back in step 1 we said x equals y? Well, that means the term x minus y is actually equal to 0. And canceling it out from both sides is the same thing as dividing by 0, which, as you know, is one of the cardinal sins in mathematics. It's a sneaky, hidden, legal move that makes the whole proof completely worthless. See, precision is everything.
So let's just quickly compare. A good proof, like that visual one we did for Pythagoras, is built on a solid foundation where every step is a valid logical deduction. A bad proof has a crack in that foundation. It could be a hidden division by 0, like we just saw, or another really common flaw called circular reasoning. That's basically when you secretly assume the very thing you're trying to prove. It's like saying, my argument is true because my argument is true. it doesn't get you anywhere.
All this focus on precision and having valid steps, it really reveals something much deeper about what math is. It's not just a collection of tools, it's really a language that has been designed from the ground up to be perfectly, unambiguously logical. Think about it. In spoken languages like English, words can have all sorts of subtle nuances and double meanings, but the language of math, it tries to eliminate all of that. Every definition is crafted so carefully to be exact and unwavering. And these super precise definitions are the bedrock, the fundamental building blocks for every single proof. Let's take the definition of a prime number. Notice that little detail in there, greater than 1? Ever wonder why the number 1 isn't considered a prime? I mean, its only positive divisors are 1 and itself, so it seems like it should fit. Well, the reason is simply a choice. Mathematicians decided to exclude 1 because it makes other more important theorems work out perfectly, like the fact that every number has a unique prime factorization. So you see, definitions in math aren't just random rules. They're carefully chosen because they're useful. And this idea is captured perfectly by a quote from one of our sources. Mathematics is a far more creative and writing-based discipline than its widely perceived role as ever more complicated arithmetic. It's not about just cranking out numbers. It's about crafting elegant arguments, choosing the best definitions, and communicating really complex ideas with absolute clarity. Okay, so why does any of this matter? Why should we care about these abstract proofs and precise definitions? Well, because this exact way of thinking is quite literally what built the modern world we live in, from our smartphones to our entire financial system. That rigorous step-by-step logic of a mathematical proof, that's exactly how a computer program works. And those prime numbers we were just talking about, their special properties are the bedrock of almost all modern cryptography. So every time you buy something online and see that little lock icon, you are using the power of number theory. This kind of abstract thinking isn't just for a classroom, it's what makes our technology possible. And if there's one thing to take away from all this, it's this. The true power of mathematics isn't just about finding an answer. It's about having the absolute certainty that your answer is correct. And not only that it's the only possible correct answer. That's the difference between a pretty good guess and an undeniable truth. So to leave you with a little taste of just how creative this can all get, chew on this mind-bending question for a minute. We know that numbers like pi or the square root of 2 are irrational. They have decimals that go on forever without repeating. So what if you take one of those irrational numbers and raise it to the power of another irrational number? Is it possible that the result could be a simple, clean, rational number? Well, the answer, amazingly, is yes. And the proof for it is one of my all-time favorites. It's just a beautiful, beautiful piece of logic that proves that such numbers must exist. But here's the kicker. It does it without ever actually telling us what those numbers are. And that, right there, is the true, beautiful, and often surprising world of mathematics.